Yes, so I want to start with the basics of the technology for those who may not have heard of VIG before. So we do have at least 2 sheets of glass, which are hermetically sealed around their edge. And in between, we actually create a vacuum, almost vacuum-like space. And through that created vacuum, we actually prevent the thermal process of conductance. And by that, we can actually reach UG values which are comparable to those of IGUs, triple IGUs, but being much more slender than in an IGU setup. And we actually even have the possibility to improve the whole system even more thermically by adding another sheet, so having a VIG and an IGU being a VIG hybrid. So the question is, it was actually quite interesting that Christoph Timm talked about vacuum glazing in his keynote speech on Wednesday, and he was like, okay, 10 years ago, he wished for the VIG to become more prominent. So the question is, why am I here today, even 10 years later, to talk about the topic? And the thing is, especially when it comes to Europe and the US, of course, you need standards in order to make the product usable in construction and buildings, and this is where we may have some lacks at the moment. So there are actually 2 standards on vacuum insulated glazing, which is the ISO 19916 part 1 and part 3, and both of them focus on thermal and sound insulation, but yeah, maybe you wonder already, there is no part 2. There was one part 2 in preparation, which should talk about mechanical performance, but in the end, yeah, it didn't come through. So at the moment, we do not have any standard which provides us design possibilities to evaluate the mechanical performance of vacuum insulated glazing. So when we want to build a vacuum insulated glazing in Germany or in Europe and the US, you actually need to go to local municipalities and try to convince them that the vacuum insulated glazing as a product is working. And when it comes to load, there are actually quite few loads. Like when you think of a normal vertical facade or window, you typically have dead load, you have the surface pressures, you have also impact. Temperature is a topic my colleague will talk about in a few minutes. When it's a VIG in a hybrid, we even have climatic loads, and we do have atmospheric pressure due to the setup as such that we do have 2 panes in between, we do have the vacuum. But so in general, we did have a research project over the last 3 years, and we considered all of those loads and brought them to an approval to build such a building in Germany. But today, I just want to focus on one of them, which is wind. But as you can already see, this atmospheric pressure cannot be neglected because due to the setup, and we hope, of course, that the vacuum will be present for a very long time, you always have this additional load of atmospheric pressure, and it's actually not negligible, but it's a permanent load of 0.1 Newton per square millimeters or megapascal, which is actually 10,000 kilograms on the unit over a square meter all the time. When it comes to wind load, what we were actually wondering, or what we wanted to answer in order to show the municipality that everything works, is we do have quite an inhomogeneous setup with the edge seal, and there are actually also some little spaces in between to withstand this atmospheric pressure. How does it behave? Does it behave like a normal monolithic, or is there something else? And if it behaves like a monolithic, can we actually find something to design it more simple than always having numerical models? So yeah, maybe like for laminated glass, having an equivalent thickness approach. So what we did Of course, on the one hand, we wanted to find out, okay, when we want to think of US and Europe, what are the typical wind loads acting on such a unit? So we actually checked the codes, and when we limited on vertical glazing, especially for residential buildings, because lots of monolithics and bad double insulated glass is still present in residential buildings, we can actually estimate 2 kilopascals of wind load is a good maximum to consider. We then, as we didn't find any VIG standard on the mechanical performance, actually oriented on the typical glass codes in America and in Europe, and came up with some resistance values around 20 megapascals. And what we then did, actually, and this is what I want to quickly present today, is we started some numerical investigations, and we actually also did some experiments in the end for our setup in the project of our demonstrator building. So I'm from university, so I have lots of time to actually make quite detailed numerical models in comparison to maybe others who cannot spend the time. So since we do have this inhomogeneous setup, we tried to put finer meshes in areas where we do have stress concentrations and actually also very, very small elements. So this is what we did. We have a more detailed mesh along the edge and through thickness and in the pillar region where actually things can happen in the case of atmospheric pressure. We started in the study with some basics, like we had only a symmetric setup with both panes being the same thickness, looking at square units. Since this all leads to a symmetric setup, and also we have symmetric loads, we can actually spend less in calculation by using a quarter model. We looked at a specific reference configuration, which is given there. You don't, it's not too important, but this is what we looked at, and we always had to look at atmospheric pressure first because it's always there, and then we added the wind load. And to just tell you why atmospheric pressure is important, here are some stresses. So we have several areas where we do have tensile stress due to atmospheric pressure, which is along the edge. But if you design the product in the right way, this can actually be prevented to get critical. We also have stresses, compressive stresses actually in the pillars, but if you use the right material, that's also not of a problem. And we have additional stress fields within the vacuum gap, but maybe you know, since we all are familiar with glass, glass likes inert conditions, vacuum environment doesn't like water, but we don't want water, and we typically don't have water in that environment. So for a first step, we can actually say if the product is designed in the right way that we don't have to think about that. So the actual area where high stresses can occur and that could also become critical is actually on the outside above the pillars. And the height of this stress is actually dependent on the separation of the pillar to each other and the glass thickness. So here you can see that it can actually even become very high. So if we have very high, large separations between the pillars, we can reach high values. So dependent on pillar separation and glass thickness. When we now look at wind, first of all, I wanted to show some center results for two different VIG units, one with 2 times 3 millimeter setup and 2 times 5 millimeter setup, which are typically used. Actually, in Asia, VIG is used very often or has been used in the past 30 years. And this is what you can typically get from manufacturers. And we considered a numerical model of the VIG, but also of a monolithic of the same thickness to see the differences. And we actually also used a simple thin plate equation to see where a linear limits lie. And what we actually found is that in areas, okay, this doesn't work, in areas where the VIG is very small, we actually are underestimating or overestimating the deflection, the linear solution underestimates the deflection, showing that the VIG may react less or softer than what you would expect from a plate. But the higher the unit gets, or the bigger the unit gets, the more nonlinear effects come into place, and the VIG actually behaves quite stiff. This is also the case for the stress, and yeah, we actually see that with a monolithic equivalent, we come quite to a good value to estimate the center stresses of a VIG. When we actually look at a linear profile, we see a little bit of different effects. So we actually consider two boundary conditions as limit cases. So of course, a frame may lay somewhere in between, but we do have completely the Navier condition, and then we have the other condition where we actually hinder bending moments, etc., at the edge. And what we see for both cases is that we have a peak at the edge due to the edge seal, and we do have quite high stresses in the case of boundary condition 2, where we hamper everything, and for boundary condition 1, we still have some stresses at the edge, and the center stresses are the same as in the center results. So yeah, we actually see that the location and the magnitude of the stresses is actually decisively influenced by the boundary condition, and it also depends on the surface. So I actually didn't say we see two surfaces. So the one is the surface where the pressure is put on, and the other one is on the other side. Yeah, if we just take the maximum value as a conservative estimate from the figure before and check it for different thicknesses and for different sizes of VIGs, and also plot the resistance side of the glass codes I was showing before, we actually see, okay, the bigger the unit gets, the more we have to add as thickness in order to meet those values of the standards. Of course, we can't forget that it's not the maximum values of the wind load only, but we always have to consider the atmospheric pressure as well. If we consider specific product with a specific pillar separation and specific thickness, we get a value here. I chose pillar separation of 40 from our reference geometry. We get about 16 megapascal of extra stress, which always has to be considered. So we see, yeah, it may look a little bit worse when it comes to meeting the standards values, but we can actually play with the thickness, and also we have products when we need them where we can temper the product, so we have a resistance side which is much above what is actually occurring. So this is how we actually can be safe that the VIG can be used according to the standards. Yeah, this is just part of the numerical simulation. So we did a huge study with lots of parameters, but that's the basics, how you can always get your design value. We also did perform some experiments on the setup we chose for our demonstration building in the project. So we also measured some stresses and deflections. And what we found there, and actually, as you can see here, we used the real frame and not those two boundary conditions, and for that setup, we actually found that the behavior compared to a real monolithic is about in the range of 90 to 95%. So if you really want to be on the safe side and have a conservative design, you can actually work with a monolithic, take a 90 to 95% of the thickness of the whole unit, and we'll get good estimates of your deflections and stresses. yeah, here actually just a little outcome of our project being this demo building, which is currently under construction, but at least we were able to convince the municipality that this VIG as a product can work in Germany. And we had a hybrid facade, so we have the VIG in an IGU unit, and there we reached UG values of 0.33. So as a conclusion, we do have a high potential when it comes to VIG because we have a slender construction, but still can get very good thermal performance. Still, we may lack especially some standards to guide us in Europe and the US to use the product. But we can show through investigations, numerical as well as experimental investigations, that the product worked. And we actually, in the experimental investigations on those units you saw there, they were like 2.5 times 1.5 meters big, and we put like 8 kilopascals of load, and it was completely fine. So we were quite confident and hope that this will also be the case in the future, that there is no problem with the occurring loads. A little outlook, because I neglected the inner surfaces in the beginning, and typically if the design is well and the producer is good, you don't have any problems with it. But what we also could see is that for some of the products you actually get contact cracks, which typically are so-called cone cracks and partial cone cracks depending on the load, and also depending on the contact friction, you can actually get quite high peaks on the inner surfaces as well. And actually, even if you see cracks there and they may look scary, typically nothing happens even if cracks are there, but you have to be a little bit cautious about that. And of course, the next step, or what we are trying to achieve, is to really have a design concept ready for the US and Europe. And typically, you, of course, want to have a very good U value, so you decide which U value you require for your building first. Then you have several parameters you can work with in order to achieve that U value by glass thickness, using annealed glass or fully tempered glass, the separation of the pillars and its material. Then, as shown before, we are trying to orient on the codes as much as possible. We have the wind load case. We can calculate with the existing standards. We do have atmospheric pressure to always add. And we also saw that an equivalent thickness solution could be nice in the future. We don't have a formula yet, so if you're interested in doing something on that, just contact us. We do have additional loads, of course, I didn't consider here, like impact. I did that, I showed that on another presentation. Temperature load, my colleague will talk about in a minute. And on that internal surfaces, we may need some more defined values in order to make sure that all the products entering the market actually are of good quality and can make a safe construction of VIG possible. So this is actually the end of my presentation. I thank you that you have been here this morning, and if you have any questions, so this is actually our project partners in the project. So we had a lot of industry partners who helped us to bring our product, or the product we use, to an approval in Germany. And yes, if you have any questions, I am happy. Thank you.